Hello everyone and welcome to this masterclass on photoelectrochemistry, or short PEC. My name is David and I'm a scientist at Redeem Technologies, where I work on the development of photoelectrochemical reactor systems and electrochemical flow technologies. So thank you all for joining today, and over the next approximately 2 hours and 20 minutes we'll explore the fundamentals, engineering principles and current developments in PEC technology. And my goal here is to provide both a theoretical understanding and an engineering perspective, so that by the end of this masterclass you have a solid overview of the field and the challenges involved in translating PEC concepts into practical systems. So to begin, let's first have a look at today's agenda. So I will start by introducing the fundamentals that govern photoelectrochemical reactor design, including the operating conditions, performance evaluation, materials and photoelectrodes, and we will move from established water splitting reactor to two emerging applications, which is organic photoelectrochemistry and also photoelectrochemical CO2 reduction. Here there are many new reactor engineering challenges, and finally I will compare these three application areas and summarize the main design principles that have emerged through the presentation. But maybe let's start with a little bit of theoretical background for people that are completely new to the field of photoelectrochemistry. Okay, let's start with briefly introducing the very basic principle of photoelectrochemistry. Let's start on the left side of the figure. So here we have a semiconductor photoelectrode, and it is immersed in an electrolyte, and when sunlight strikes the semiconductor, a photon with sufficient energy is absorbed and creates an electron-hole pair. The hole, which is the positive charge carrier, migrates to the semiconductor surface, where it drives an oxidation reaction. In this example, water is oxidized to oxygen. The electron, on the other hand, travels through the semiconductor into the external electrical circuit and reaches the counter electrode on the right. And there it participates in a reduction reaction, where protons from the electrolyte are converted into hydrogen gas. Meanwhile, ions inside the electrolyte maintain charge neutrality by completing the internal circuit. So in summary, photoelectrochemistry converts solar energy directly into chemical energy by spatially separating oxidation and reduction reaction. Okay, and to understand how these semiconductors in photoelectrochemical devices work, we first need to look at the electronic structure of materials, because in an isolated atom, electrons occupy discrete energy levels. However, when a large number of atoms comes together to form a crystal, these individual energy levels split and overlap, creating a nearly continuous energy band. And the two most important bands here are the valence band and the conduction band. The valence band contains the electrons that are normally involved in the chemical bonding and is typically filled with electrons. And the conduction band lies at a higher energy level and is usually empty. And electrons that gain enough energy, for example by absorbing light, can be excited from the valence band into the conduction band, where they become mobile and can participate in electrical conduction and electrochemical reactions. So, and to understand why semiconductors are used in PEC, we first need to look now at their specific electronic structure. So look at the diagram here. Let's start with an insulator. Here the valence band and conduction band are separated by a very large band gap, and electrons cannot easily gain enough energy to close this gap. So the electrical conductivity is extremely low. And then in the middle here we have the semiconductors, and they are different because their band gap here is much smaller, and under normal conditions they are poor conductors, but when they absorb light with sufficient energy, electrons can be excited from the valence band into the conduction band. So this leaves behind positively charged holes, giving us the electron hole pairs we discussed in the previous slide. And finally, in metals, the valence and conduction band, they just overlap, so there's no gap. Electrons can move freely here without any external excitation, and this is why metals have such a high electrical conductivity. And for PEC applications, semiconductors provide exactly the balance that we need because they are stable in the dark but become electrically active when illuminated, especially in the range of visible light. So now that we know what a band gap is, the next question is, when does light actually create charge carriers? And the answer depends on the energy of the incoming photon, which is given by E equals h₂, with h the Planck constant and nu the frequency. So if the photon energy is smaller than the band gap, the electron cannot reach the conduction band, and the light is therefore not absorbed but simply passes through the material. This is why materials with large band gaps like glass, for example, are transparent in the visible range. And if the photon energy matches or exceeds the band gap, the electron is excited into the conduction band, leaving behind a hole in the valence band, and this is the charge separation that drives photoelectrochemical reactions. Metals behave differently because they have no band gap. So electrons can interact with photons over a broad energy range. So light is mainly either reflected or absorbed rather than transmitted. And this is why metals can never be transparent. For photoelectrochemistry, this means that the band gap has to be carefully chosen. It has to be small enough to absorb a large fraction of sunlight, but large enough to still provide sufficient driving force for the desired reaction. And now that we understood how the photoelectrode generates these electrons and holes, we can look at the reaction we want to drive. For overall water splitting, the net reaction is simply the conversion of water into hydrogen and oxygen using sunlight. And the 4 absorbed photons ideally provide the 4 charge carriers needed for one reaction cycle. One important practical point is that pure water is actually a very pure electrolyte. Its conductivity is around 10 to the power of -6 Siemens per centimeter, whereas a typical 1 molar KOH solution reaches about 1 Siemens per square centimeter, so roughly 1 million times more higher. Without an electrolyte, the ohmic resistance would simply be too high for efficient operation. And now on the right side, the exact half reactions depend on whether the electrolyte is acidic or alkaline. The overall reaction stays the same, but the charge carriers differ. So in acidic media, protons are transported, while in alkaline media, hydroxide ions are involved. And in practice, alkaline electrolytes as KOH are used more frequently because they provide high conductivity and are compatible with many of the most stable photoelectrode materials. In contrast to this, acidic media is more established in classical electrolysis, but often needs precious metal electrodes. This is why they also want to get away from that. Now that we know the overall reaction, the next question is, what properties must a semiconductor actually have to drive water splitting in particular? So in theory, 2 conditions have to be fulfilled. First, the valence band must be positive enough to oxidize water to oxygen. And second, the conduction band must be negative enough to reduce protons to hydrogen. This means the band edges have to straddle the 2 water redox potential, giving a theoretical minimum band gap of 1.23 electron volts. However, 1.23 electron volt semiconductor is usually not sufficient in practice. So in real reactions, we suffer from kinetic limitations and so-called additional voltage, and this is called the overpotential, which is required. A simple analogy here is when you push a heavy object. So in theory, only a certain force is required, but in reality, you need to give it that extra push to overcome friction. And the overpotential is exactly this additional energy needed because real electrochemical systems are not ideal. And as a result, single absorber photoelectrochemical devices typically require a larger band gap around 1.8 to 2.4 electron volts. And this provides enough photovoltage to drive the reaction while still absorbing a useful fraction of the solar spectrum. So on the right here, the equation shown reminds us that the maximum photovoltage or open circuit voltage is always smaller than the semiconductor band gap divided by the elementary charge. In other words, not all of the band gap energy can be converted into usable voltage, which is another reason why practical devices require larger band gaps than the theoretical minimum. Just to add to this, to better understand where this additional voltage comes from, the overpotential is not a single loss mechanism. It is the sum of several different contributions. The first is the activation overpotential. So every electrochemical reaction has an energy barrier that must be overcome before electrons can be transferred efficiently at the electrode surface. The second is the ohmic overpotential, which simply comes from electrical resistance in the electrolytes, the electrodes, and all electrical contacts. The third is the concentration overpotential. If reactants cannot reach the electrode fast enough or products are removed too slowly, mass transport becomes the limiting factor and additional voltage is required. And finally, in water splitting, especially gas bubbles introduce another important loss. So hydrogen and oxygen bubbles can block the active surface area and reduce the contact between electrolyte and the electrode. And this increases the effective resistance, and these four contributions explain why practical PC devices always require more than the theoretical 1.23 volts, and why reactor engineering is just as important as catalyst development here to overcome this. We've seen now how light generates an electron-hole pair, so let's follow what happens to these charge carriers on their way to forming hydrogen and oxygen. So look at the picture on the right here. A photon is absorbed inside the semiconductor and creates an electron-hole pair. The electron travels toward the back contact, while the hole has to reach the semiconductor surface where it oxidizes water to oxygen. However, the charge carriers do not survive indefinitely, so they can recombine before reaching the surface, which means their energy is lost as heat instead of driving the reaction. So look here at the formula with LD. The average distance a charge carrier can travel before recombination is called the so-called diffusion length, LD. It depends on how fast carriers move and how long they survive, as shown by the equation here. This creates a fundamental design trade-off. The photoelectrode has to be thick enough to absorb sufficient light, but thin enough that most charge carriers can still reach the surface before recombining. And now look at the table here, because different materials have very different diffusion lengths. Hematite, for example, has extremely short diffusion length and only a few nanometers, whereas crystalline silicon reaches hundreds of micrometers, and this strongly influences the reactor geometry and the photoelectrode architecture that can be used. So ideally, the photoelectrode thickness should be therefore on the order of the diffusion length to maximize the charge collection. And the natural question that follows from this is, what is if the diffusion length is much shorter than the thickness needed to absorb enough light? And here in this picture we see a flat bulk photoelectrode where the charge carriers are forced to travel through the entire thickness of the material before they reach the surface. And for materials with short diffusion length, many carriers recombine before they can participate in the reaction. So nanostructuring provides a solution by decoupling light absorption from charge transport. So if you look at the bottom picture here, the light still is absorbed over the full thickness of the electrode, but the generated charge carriers only need to travel a short radial distance to reach the semiconductor electrolyte interface. And this greatly reduces recombination losses and makes materials with shorter diffusion lengths, such as hematite or copper oxide, much more practical. The SEM images here illustrate this concept with copper oxide, and the upper image shows a compact thin film, whereas the lower image shows a nanorod array with much larger active surface area. However, this nanostructuring also introduces a new challenge, because here the larger surface area creates more surface states where recombination can occur. So charge transport between individual nanostructures can increase resistive losses, and these complex architectures are generally more difficult to manufacture and scale up and also stabilize for long-term operation. So nanostructuring is not a universal solution, it's more of a trade-off between improving charge collection and increasing structural complexity. So let's assume our photo-generated charges have successfully reached the semiconductor surface. The next question now is, can they actually make it through the entire device without losing too much energy? And that brings us to series resistance. So resistance simply describes how strongly a material opposes the flow of electric current. And even if we generate plenty of charge carriers, every resistance inside the cell consumes part of the available voltage, leaving less voltage to actually drive the electrochemical reaction. So if you look at the list on the left, the total series resistance is the sum of several individual contributions. So first we have the semiconductor itself, then the transparent conductive oxide or TCO layer, which is usually FTO, we will talk about that later. We also lose voltage at the electrical contacts, and finally in the electrolyte due to ionic resistance. And all of these contributions add up to the total series resistance, which is Rs. So when we look at the formula here on the right, according to Ohm's law, the voltage loss is simply the current multiplied by the series resistance. And this voltage loss is commonly referred to as IR drop. And at laboratory current densities of around 10 milliamps per square centimeter, these losses often are relatively small, but the situation changes when we move toward industrially relevant current densities of 100 to 500 milliamps per square centimeter. Since the current increases by 1 to 2 orders of magnitude, even a modest resistance here can consume hundreds of millivolts. And here, if you look at the red box at the bottom, the rule of thumb is we try to keep the IR drop below about 100 millivolts. Beyond that, a significant fraction of the generated photovoltage is simply wasted overcoming resistance instead of driving chemistry. So now to explain what the TCO layer is, the upper sketch shows what happens without these TCO layers. The electrons generated far away from the metal contact have to travel laterally through the semiconductor before they can be collected. And since most photoelectrode materials are relatively poor electrical conductors, this creates high series resistance. And then below that, with a transparent conductive oxide underneath the semiconductor, electrons only need to travel a very short distance vertically before entering the highly conductive TCO layer, and from there they are transported laterally with much lower resistance to the metal contact. So in other words, the TCO acts like a current collector. It is transparent enough to let the light reach the semiconductor, while simultaneously providing a low resistance pathway for charge collection. So once the charge carriers reach the semiconductor surface, the next bottleneck is no longer inside the solid, but in the electrolyte. So on the graphic here on the right, when current flows, reactants at the electrode surface are continuously consumed, and therefore they have to diffuse from the bulk electrolyte towards the electrode. So look at the diffusion layer here. This creates a concentration gradient known as diffusion layer, and close to the electrode the reactant concentration is lower than in the bulk solution. And now when we look at this formula, then we see that the maximum current that can be sustained by diffusion alone is called the limiting current density, shown here by this equation. The important parameter for reactor design is the diffusion layer thickness delta. A thinner diffusion layer always allows faster mass transport and therefore supports higher current densities. And in stagnant electrolytes, the diffusion layer is typically between 100 and 1000 micrometers thick. So this is very thick. Under flow conditions, it can be reduced to only a few micrometers, up to around 100 maybe. And this is one of the major reasons why flow reactors generally outperform any batch reactor at high current densities. So convection continuously replenishes the reactant at the electrode surface. And to give a little more in-depth view on diffusion versus convection, so here if transport relies only on diffusion, the ions move solely because of concentration differences, and this is a relatively slow process, especially close to the electrode where reactants are continuously consumed. So over time the concentration gradients become smaller and diffusion alone cannot supply reactants fast enough for high current densities. And by introducing convection, either through stirring in batch, for example, or continuous flow in the flow cells, a fresh electrolyte is constantly brought to the electrode surface. And this continuously refreshes the reactants, and this reduces the diffusion layer thickness and significantly increases the achievable mass transport. And as a result, as we learned previously, higher current densities become possible, while the reactor also operates more stable. And now that we have established that we need convection, the question is now how we create the convection in the reactor. And if we look at the top flow bioreactor here, the simplest approach, here the electrolyte flows parallel to the electrode surface, and convection mainly occurs in the bulk flow, while the final transport to the surface still relies on diffusion through a diffusion layer. So in the red window here, we see as a result only a relative thin region close to the electrode remains diffusion controlled. If we now look at the bottom flow reactor, here we have a flow through reactor, and the electrolyte is forced directly through a porous electrode, and this creates convection inside the electrode structure itself. And if we look in the little red zoom window, instead of only transporting species parallel to the surface, reactants are continuously supplied throughout the entire porous network. This greatly shortens the diffusion distance. So if we look at the table below, consequently flow through electrodes achieve thinner diffusion layers, utilize a much larger active surface area, and generally allow faster reaction kinetics. The trade-off here is a higher pressure drop and a more complex reactor design compared to a conventional flow bicell. So both concepts are used in PEC systems, but the choice depends on whether simplicity or maximum mass transport is the primary design objective. And mass transport influences more than just the reactant concentration. It also changes the local chemical environment directly at the electrode surface. So here on the left, whenever electrochemical reactions occur, protons or hydroxide ions are either consumed or produced. And as a result, the local pH close to the electrode can differ significantly from the bulk electrolyte. So here, for example, oxygen evolution generates protons, making the local environment more acidic, and hydrogen evolution consumes protons, making the local pH higher. And why does this matter? Because the local pH changes influence several important aspects of the reactor performance. They affect the reaction kinetics, also the stability of your photocatalyst and the membrane performance, and ultimately the overall efficiency of the whole PEC device. So here the graphic on the right. In addition, semiconductor band edges shift by approximately 59 millivolts per pH unit as described by the Nernst equation. And although both semiconductor band edges and the electrochemical redox potential shift with the pH, real devices still show performance changes because of reaction kinetics, surface chemistry, and overpotentials. They are all strongly pH dependent. So this is another reason why good electrolyte management and efficient flow are essential, not only to improve mass transport, but also to maintain a stable local reaction environment. So the final transport limitation then appears once the reaction products leave the electrode as a gas. So unlike dissolved species, hydrogen and oxygen first form bubbles on the electrode surface, and these bubbles go through 4 characteristic stages. So first, these bubbles nucleate once the dissolved gas concentration exceeds the local saturation limits. Then they grow by diffusion as more gas is produced. Then the critical step is the bubble detachment, and if bubbles remain attached for too long, they just begin to cover active surface area sites, and in PEC systems they also can block incoming light. And finally, the bubbles have to be transported away from the electrodes. If they accumulate, they can increase the mass transfer resistance, increase ohmic losses, and reduce the effective reaction area here. And there are several engineering strategies that can promote early bubble removal. The surface wettability can be tuned to reduce the detachment diameter. Vertical electrode orientation allows buoyancy to assist the removal, and electrolyte flow actively sweeps bubbles away. And dedicated flow paths can prevent bubbles from becoming trapped. So in other words, a successful PEC reactor design is not only about generating gas efficiently, but also removing it efficiently. Now I'd like to summarize the transport limitations that we've discussed. So the important point here is that not all transport limitations dominate at the same operating current density. So inside the semiconductor, charge carriers are the first limitations at low current densities. Recombination and finite diffusion length can here dominate. And as current density increases, electrical series resistance in the semiconductor, the TCO layer, and the contacts become increasingly more important. Then in the middle here, in the electrolyte, low current densities are mainly affected by ohmic losses, and at higher current densities, concentration gradients and local pH changes become the dominant limitations. And then at the bottom, finally, in the liquid phase, diffusion through the boundary layer limits transport initially, but once significant amounts of hydrogen and oxygen are produced, bubble accumulation and gas removal become the major bottlenecks. So the dashed line here marks approximately 1 sun operation, corresponding to about 8 milliamps per square centimeter for an ideal PEC device. And around this point, almost all transport processes begin to interact, but as we move forward towards industrially relevant current densities like 50, 100, or even several hundred milliamps per square centimeter, transport engineering becomes just as important as the photoelectrode material itself. Now that we've established the fundamental transport limitations in photoelectrochemical systems, we can move on to the practical engineering side. So in this chapter, we look at the operating conditions that directly influence these transport processes and ultimately determine the reactor performance. First operating parameter I'd like to discuss is the light management, because without efficient light delivery, none of the subsequent transport processes can take place. So if you look at the graphic here in the middle, there are 2 fundamental ways to illuminate a photoelectrode. In back illumination, shown on the left, light first enters through the transparent substrate and then the transparent conductive oxide, or TCO, before reaching the photoactive semiconductor. The major advantage is that the light never has to travel through the electrolyte. So that means there's much less interference from gas bubbles and the optical path remains well controlled. The disadvantage is that the TCO can absorb a small fraction of the incoming light, and in addition, the lateral current has to travel through the TCO layer, making resistive losses increasingly important for large area devices. And in front illumination, the situation is reversed. The light enters through the electrolyte first and reaches the photoelectrode directly. So this avoids optical losses in the substrate and also means the current collector no longer has to be transparent, giving much more flexibility in electrode design. However, the electrolyte itself can absorb part of the light, and perhaps more importantly, the hydrogen and oxygen bubbles directly in the optical path, and they can partially shade the photoelectrode. So ultimately, there is a trade-off between electrical and optical performance. So front illumination generally provides better electrical architecture, whereas back illumination offers the more stable optical conditions. Which configuration is preferable depends on the specific reactor design and operating conditions. Even after choosing the illumination direction, not all incident light is actually reaching the photoactive material. So every optical loss that occurs before photons are absorbed is irreversible because no electron hole pairs can be generated from photons that never arrive at the semiconductor. So this is important because optical losses directly reduce the maximum achievable photocurrent and therefore the overall efficiency of the reactor. And even reflection at interfaces can cost several percent of the incoming light. And as current density increases, gas bubbles and the electrolyte introduce additional optical losses, while thick and opaque catalyst layers on top of the semiconductor can further reduce the amount of light reaching the absorber. The main optical loss mechanisms can be grouped into 4 categories. So first, reflection at interfaces such as air glass and TCO layers. Second, parasitic absorption, where light is absorbed by components like the TCO, the catalyst coatings, or anything else instead of the semiconductor. Third, absorption within the electrolyte itself, which becomes particularly relevant for strong absorbing electrolytes or long optical path lengths. And finally, scattering by hydrogen or oxygen bubbles, which increasingly becomes a problem as the reaction rate increases. So the key message is that the reactor design should deliver as many photons as possible to the active semiconductor while minimizing every unnecessary optical loss along the way. And one strategy to reduce optical losses is actually light trapping. So here on the left, instead of allowing photons to simply pass through the photoelectrode, the surface is intentionally textured or nanostructured so that the incoming light is scattered in multiple directions. And this effectively increases the optical path length inside the absorber. And as a result, each photon has a higher probability of being absorbed before leaving the material. The 2 major advantages are therefore a higher photon absorption and reduced transmission losses, allowing thinner photoelectrodes to absorb as much light as much thicker planar films, like in the graph below. So this is illustrated here. An optimized light trapping structure approaches the Jablonowicz limit, meaning significantly higher absorption over a broad wavelength range compared with a simple single pass absorber. And now on the top right, the effectiveness of the light trapping strongly depends on the relationship between the wavelength of light and the characteristic size of the surface features. So if the structures are much smaller than the wavelengths, the surface behaves almost like an effective medium. If they are much larger, only weak diffraction occurs. And the strongest light trapping is achieved when the feature size is on the order of the wavelengths, where diffraction and resonance scattering become most effective. So if you look now at the red box, there you can see that there is an important trade-off again. Capturing more photons is only beneficial if the generated charge carriers can still be collected efficiently. So increasing the surface area means again also increasing the probability of surface recombination. We talked about this before. While the diffusion length inside the semiconductor remains unchanged. So in addition, highly textured electrodes may introduce additional parasitic absorption. So maximizing optical absorption alone does not guarantee higher photocurrent. An efficient PEC electrode must always balance light management with charge collection. The next important operating parameter is the electrolyte, because it not only transports ions between the electrode, but also strongly influences reactor resistance, cell design, and even which photoelectrode material can be used. So the simplest approach is using a liquid electrolyte. Liquid electrolytes offer high ionic conductivity, are easy to implement, and generally provide a lower resistance, especially at higher electrolyte concentrations. However, the electrolyte spacing becomes an important design parameter. So if you look at the picture here on the left cell, if the inter-electrode gap is too large, ions have to travel longer distances, increasing the ohmic resistance. On the other hand, if the gap becomes so small, gas bubbles can become trapped between the electrodes, increasing the pressure drop and potentially blocking mass transport completely. And this is one of the reasons why zero gap architectures, like here in the picture on the right, become increasingly popular. So here the electrodes are brought as close together as possible, only separated by an ion conductive membrane. And this minimizes ionic resistance while maintaining efficient ion transport. And so these zero gap designs, they are often coupled with reduced leakage, and they improve also the mechanical stability, but the trade-off is increased system complexity, since you need porous electrode and good membrane electrode interfaces here. So if you look at the table at the bottom, the electrolyte pH also plays a major role in material selection. So many photoelectrode materials are only chemically stable within a limited pH window. So for example, acidic electrolytes often require noble metal catalysts, whereas many transition metal oxides, including hematite or nickel oxide, perform much better under alkaline conditions. So when selecting the electrolyte, we're not only choosing the ionic conductor, but simultaneously determining the reactor architecture, the achievable resistance, and the range of compatible photoelectrode materials. Another natural question at this point is, if light generates charge carriers, then why don't we simply increase the light intensity indefinitely? And under standard testing conditions, PEC devices are typically characterized under one sun illumination corresponding to about 100 milliwatts per square centimeter, and depending on the material, this results in a photocurrent density of roughly 8 to 25 milliamps per square centimeter. So increasing the light intensity has several advantages. So more photons generate more electron hole pairs, increasing the photocurrent and therefore the hydrogen production rate per unit area. The additional heating can also improve reaction kinetics and reduce the external bias required for water splitting, and solar concentrators can partially compensate even for fluctuations of natural sunlight. And if we look now at this picture, here there are many reactor concepts where they have explored optical concentration using mirrors or lenses. Here the reactor position is always highlighted in red, and the path of the sunlight are the yellow arrows. And these examples include parabolic through collectors, Fresnel collectors, compound parabolic concentrators, and many more. In each case, the PEC reactor is positioned at the focal region where the light intensity is the highest. However, more light does not automatically translate into proportionally more current. So at higher proton fluxes, recombination increases because charge carriers are generated faster than they can be transported away. And at the same time, the transport limitations we discussed earlier become increasingly important. So mass transport, ionic transport, and bubble removal eventually become the bottlenecks, meaning the photocurrent begins to saturate instead of increasing linearly. And in addition, the higher temperature and photon flux can accelerate material degradation, creating long-term stability issues. So these concentrated PEC reactors, they also have to cool it actively to counteract this. So this is why I like to revisit the transport hierarchy here from the previous chapter, but now from the perspective of operating conditions. So the key message is that not every PEC reactor should be designed the same way. The optimal reactor architecture depends strongly on the current density it is expected to operate at, which in turn is largely determined by the illumination intensity. So for example, under moderate solar concentration around 6 suns, the photocurrent increases to roughly 60 milliamps per square centimeter. So at this point we begin to move away from a regime dominated by charge transport limitations inside the semiconductor, and instead the ionic transport, local pH gradients and bubble removal become increasingly important. If we further increase the light intensity to around 40 suns, current densities can approach like 240 milliamps per square centimeter. And now the dominant bottlenecks are completely different. So series resistance in the TiO₂ and electrical contents become very significant, and the bubble management becomes critical. And maintaining uniform electrolyte composition becomes much more difficult. So to summarize, increasing the photon flux shifts the limiting transport processes from the semiconductor towards the electrolyte and finally into the gas phase. And this means there's no universally optimal PEC reactor. A reactor designed for one sun operation is not necessarily suitable for concentrated sunlight because the dominant engineering challenges fundamentally change. The following section therefore focuses on how operating parameters such as pressure and temperature can be tailored to match the intended operating regime. So at first glance, increasing the temperature seems beneficial for almost every electrochemical process. So at the left here, higher temperature accelerates reaction kinetics, improves ionic conductivity, and often increases even the charge carrier mobility in the semiconductor. And as a result, we usually observe higher photocurrents and lower kinetic overpotentials. So performance generally improves as the temperature increases. And if we look now in the middle, then we see that this only holds up to a certain point. So higher temperature can also promote unwanted processes. Charge recombination can increase. Catalysts and photoelectrodes degrade faster, and therefore the long-term stability suffers. So while the initial performance may improve, the overall efficiency and device lifetime can actually decrease. And because of these competing effects, PEC systems typically exhibit an optimum operating temperature rather than simply the hotter the better. So for many semiconductor systems, this optimum lies somewhere around 40 to 60 degrees Celsius, although the exact value depends strongly on the photoelectrode material and the electrolyte. So in practice, reactor temperature therefore becomes another optimization parameter that must balance performance, efficiency, and long-term stability. So the final operating parameter I like to discuss is the pressure. So interestingly, pressure affects the oxygen and hydrogen side quite differently. On the oxygen evolution side, relatively moderate pressures of around 2 to 3 bars are often sufficient. Also ambient pressures can be fine, but increasing the pressure reduces the bubble size, which lowers bubble-induced resistance and decreases optical scattering at the illuminated photoelectrodes. So on the anode side, pressure is mainly used as a tool to improve reactor operation rather than to create a direct economical value. The hydrogen evolution side is a different story. So here pressure between roughly 5 and 30 bars are common considered because the hydrogen is produced already pressurized, and that significantly reduces the energy required for downstream gas compression, which is one of the major operating costs in hydrogen production and can be directly seen on the price for the hydrogen. Another attractive possibility is here operating with a tri-hydrogen compartment, because this simplifies the gas handling and reduces here the need for high pressure liquid pumping on the catholyte. So of course these advantages come then with an engineering challenge, because the reactor must not only safely withstand pressure, but also a pressure difference between the hydrogen and oxygen compartments, while maintaining optical access and a reliable design. So especially in PEC systems with a window, which all of them should have, this can become mechanically limiting at elevated pressures. Now that we've covered the operating principles of photoelectrochemical system, the next question would be how to quantify their performance. So this chapter introduces the most commonly used performance metrics and electrochemical measurement techniques. So before discussing performance metrics, we first need to distinguish between two fundamentally different operating modes of PEC systems. So the first is externally biased operation, which is by far the most common configuration in literature. And here the photo voltage generated by a single semiconductor is usually insufficient to drive the overall water splitting on its own. Therefore, an additional voltage is supplied either by an external power supply or by coupling the PEC electrode to a separate photovoltaic cell. And this allows us to study the photoelectrode under well-controlled conditions, but the system is no longer driven solely by sunlight. And the second operating mode is bias-free operation. So here the entire driving voltage is generated internally from sunlight. This can only be achieved by using tandem absorbers or by integrating a photovoltaic component directly into the PEC device. So bias-free operation is therefore much more challenging, but it represents true artificial photosynthesis because no external electrical energy is required. And now here in the red box, this distinction is important when comparing reactor performance. If an external bias is applied, we normally evaluate the system using the applied bias photon to current efficiency, or ABPE. And for completely bias-free operation, the appropriate metric is the so-called solar to hydrogen efficiency, or STH. The next slide will explain both metrics in more detail. To compare different photoelectrochemical systems, several performance metrics are commonly used, and the most comprehensive one is the so-called solar to hydrogen efficiency, or STH. It describes how efficiently the incident solar light is converted into the chemical energy stored in hydrogen, and is therefore the key metric for bias-free water splitting devices. Another important parameter is the Faradaic efficiency, as you can see below. This tells us what fraction of the measured current actually produces the desired reaction product, the hydrogen. An ideal system has a Faradaic efficiency of 100%, meaning that every electron contributes to hydrogen or oxygen production, and lower values indicate losses to competing side reactions or ohmic heating, for example. Finally, the photocurrent density is an essential input for calculating the STH in the first place. It represents the current generated under illumination, but it's important to subtract the dark current before using it in the calculation, because otherwise currents originating from non-photo-induced electrochemical process would be included, and this leads to an overestimation of the true photoelectrochemical performance. And if we have to apply an external bias, we usually evaluate the system using the so-called applied bias photon to current efficiency, or ABPE. The idea is very similar to the STH efficiency, but now we also take the applied voltage into account. Since part of the energy comes from an external power source, the efficiency has to reflect that. So the photocurrent density and Faradaic efficiency are determined exactly as before. The only difference is that the ABPE equation includes the applied bias, allowing us to evaluate the overall performance of a biased photoelectrochemical system. So in general, STH is used for bias-free devices, while ABPE is preferred metric whenever an external bias is required. And when we are characterizing photoelectrochemical materials, we can either use a 2-electrode or a so-called 3-electrode configuration. In a 2-electrode setup, the voltage is measured between the working electrode and the counter electrode. This configuration is simple and closely resembles the operation of a complete PEC device. For fundamental material characterization, a 3-electrode setup is usually preferred. In addition to the working and counter electrode, here it includes a so-called reference electrode, which provides a stable and well-defined reference potential. So this allows us to accurately control and measure the potential of the working electrode independently of the current flowing through the cell. The working electrode is where the photoelectrochemical reaction takes place, so this should be photoactive in our case, and where the material under investigation is deposited. The counter electrode simply completes the electrical circuit and carries the balancing reaction. Typically we use an inert material with low overpotential against hydrogen, such as platinum. And a common reference electrode is depicted here on the right, which is the silver chloride electrode. So this consists of a silver wire coated with silver chloride that's immersed in a saturated potassium chloride solution and connected to the electrolyte through a porous junction. The equilibrium between silver and silver chloride provides a stable and reproducible reference potential, make it one of the most widely used reference electrode in electrochemistry. Important here is that you have to choose your reference electrode depending on your solvent, because not every system works for every solvent. And a silver chloride reference electrode is usually for aqueous solutions. So in short, 3-electrode measurements tell us how good an individual electrode is, while the 2-electrode measurements tell us how well the complete photoelectrochemical cell performs. So both are important, but they answer different questions, and I've highlighted this in the bottom of this slide. So the performance of a photoelectrochemical reactor depends not only on the photoelectrode itself, but also on the materials used throughout the entire system. So in this chapter, we are looking at the key considerations when selecting materials for the different reactor components. At its core, every PEC reactor has to perform several tasks simultaneously. It has to deliver efficiently light to the photoelectrode, provide a pathway for electrons to go through an external circuit, sometimes it's internal, transport ions through the electrolyte or membrane, and generate hydrogen and oxygen in separate compartments. And the last point is important because producing hydrogen and oxygen separately is much simpler and significantly safer than generating a mixed gas stream and separating it afterwards. So separating hydrogen and oxygen after they have already been mixed is both energy intensive and also technically challenging. So most reactor designs aim to keep the two products separated from the very beginning. Beyond these core functions, a practical reactor should also minimize electrical losses, remain chemically and also thermically stable over long operating times, should provide good flow management for reactants and products, and allow the operating conditions such as pressure and temperature to be monitored and controlled. For research applications, it may also include a reference electrode for precise electrochemical measurements. So let's start with the reactor body maybe. On the right side, you can see a picture of our Redeem PEC cell body. And although this doesn't take part in the photoelectrochemical reaction itself, it has a major impact on the overall reactor performance. It needs to electrically insulate the electrodes, keep the system gas and liquid tight, and withstand the electrolyte, operating temperature, and UV light. In the lab, materials like PEEK or PMMA or 3D printed polymers are popular because they are easy to machine and great for rapid prototyping. For industrial systems, stainless steel is often preferred because it's strong, durable, and also scalable. At the same time, weight becomes an important consideration during scale up. For example, if reactors are installed on rooftops or integrated into buildings, reducing the overall weight can simplify the installation and lower the structural requirements. So also here, materials like PEC can be very relevant. Next, let's talk about sealings. They play a critical role in every PEC reactor. The main purpose here is to prevent gas or liquid leakage, keeping hydrogen and oxygen separated, and protect the system from contamination from the outside. And this is essential for both safety and product purity. And in most reactors, sealing is just achieved through O-rings or gaskets. And the material has to withstand the operating pressure, temperature, and also the chemical environment. And that's why the seal material is always selected based on whether the reactor operates under acidic or alkaline conditions. Next, the optical window is the entry point for sunlight, so its main job is to transmit as much light as possible while minimizing reflection and absorption. Ideally, the transmittance should be above 90% across the relevant wavelength range, and quartz offers the best optical performance, but it's also the most expensive option. And depending on the application, materials such as borosilicate glass or UV transparent polymers can provide a good compromise between performance and cost here. And more recently, more and more 3D printed windows have become attractive for rapid prototyping, although they still have lower transmission and lower pressure resistance. And one important point here is that the optical window is usually the mechanical weak point of the reactor. So as the window area increases during scale up, it becomes increasingly difficult to withstand elevated pressures without increasing the window thickness or adding a mechanical support. So in practice, the window design is always a compromise between optical transmission, mechanical strength, cost, and scalability. Another key component of photoelectrochemical reactors are the membranes. So their primary role is to keep hydrogen and oxygen separated while still allowing ions to pass between the two compartments. This prevents gas crossover and improves the product purity and is essential for safe operation. And depending on the electrolyte, different membrane types have to be used. Cation exchange membranes such as NiFeOx transport protons and are typically used in acidic systems, and anion exchange membranes such as fumacet transport hydroxide anions and are used in alkaline electrolytes. Alternatively, you can also use porous separators such as Surfon, and they mainly provide physical separation while allowing ion transport through the electrolyte. However, membranes also introduce an additional resistance to the cell. So as shown by the equation on this slide, this resistance increases with membrane thickness and decreases with ionic conductivity. That's why from an engineering perspective, we aim for membranes that are as thin as possible while providing sufficient mechanical strength and low gas crossover. Also, try to remember we want pressure differences in the anode and cathode compartment, so the membrane has to be able to withstand these pressure differences. And besides conventional ion exchange membranes, there are also more advanced concepts. There's the example of bipolar membranes, which combines a cation and an anion exchange layer, and this allows each electrode to operate in its optimal pH medium while maintaining a pH gradient across the membrane. The downside is the significantly higher membrane resistance, and this results in larger ohmic losses. Another interesting concept is the membraneless reactor. So here hydrogen and oxygen are kept apart purely by carefully controlling the electrolyte flow. In principle, this reduces material cost and eliminates the membrane resistance. However, it requires a very precise flow control and only works with dissolved gases rather than gas bubbles. And there's always a risk of gas crossover, and so far these concepts have mainly been demonstrated in simulations and a few proof of concept studies, but never shown in real applications. Another material of choice for the PEC cell is the electrode substrate. So this provides mechanical support and electrical connection for the photoelectrode. And it therefore has to be conductive, chemically stable, and also mechanically robust. The main design decision here is whether the substrate needs to be transparent or not. So transparent conducting oxides such as indium tin oxide or fluorine doped tin oxide allow light to reach the semiconductor through the substrate, but are significantly less conductive than metals. If you use metal substrates such as stainless steel or titanium, they often offer much lower electrical resistance and are well suited for large-scale applications in this sense. The downside, of course, is that they are more opaque and therefore require a front illuminated reactor design, and the compromise here is to use metal meshes or porous metal substrates, because these can still allow part of the light to pass through while providing much better electrical conductivity than transparent conducting oxide coated on glass, although their optical transmission is naturally lower, of course. There are a few advanced substrate designs that have been proposed to overcome the limitations of conventional transparent conducting oxides. One approach is to integrate metal grids or meshes into the substrates, and these reduce the current path through the TCO and therefore lower the overall sheet resistance while still allowing most of the light to reach the photoelectrode. Other concepts include, for example, carbon paper or membrane electrode assemblies, as well as multi-electrode designs, where the illuminated area is divided into several smaller photoelectrodes connected in parallel. So this shortens the electron transport distance and helps reduce resistive losses, especially as the devices increase in size. And these concepts become increasingly important during the scale-up, when the resistance of large transparent electrodes can otherwise become a major performance limitation. Now, with the reactor components covered, let's now focus on the heart of every photoelectrochemical system, which are the photoelectrodes. We briefly look at the most widely used materials for photoanodes and photocathodes, as well as some of the emerging materials that are currently attracting attention in research. But the goal in this chapter is not to provide an in-depth discussion of photoelectrode fabrication or manufacturing techniques. Instead, it is intended as a reactor engineering perspective, highlighting the material properties that are most relevant for reactor design, integration, and overall device performance. So before we look at individual materials, it's important to understand the theoretical limits of photoelectrodes. For example, for single absorbers, there's always a trade-off. A small band gap allows the material to absorb more sunlight, but it doesn't generate enough voltage for water splitting. A larger band gap provides more voltage but absorbs a smaller fraction of the solar spectrum. So as a result, there is an optimum, and that's around 1.6 to 1.8 electron volts, giving a practical maximum SDH efficiency of roughly 10 to 12%, as shown in this graph here on the right side. Tandem absorbers can overcome this limitation by combining two semiconductors with different band gaps. So the top absorber captures the high energy photons, while the bottom absorber utilizes the lower energy part of the spectrum. And this reduces thermalization losses and makes much better use of the available sunlight. So as a result, tandem devices can theoretically reach 25 to 30% SDH efficiency, making them one of the most promising approaches for high efficiency photoelectrochemical water splitting. So, and this slide shows now how the theoretical efficiency limit can be estimated from the band gap. So an example here, hematite has a band gap of about 2.1 electron volts, so it can absorb photons with wavelengths up to roughly 519 nanometers. When we integrate the solar spectrum and count all the photons with an energy equal or greater than this band gap, Under ideal conditions, this gives us a maximum photocurrent density of about 12.5 milliamps per square centimeter, and we can insert this value in the SDH equation using the thermodynamic water splitting potential of 1.23 volts and an incident solar power of 100 millivolts per square centimeter, and this gives an idealized efficiency of roughly 16%. However, this calculation assumes perfect light absorption, also perfect charge collection, no recombination, no resistive losses, and no overpotential. So once realistic voltage requirements and other losses are included, the practical single absorber limit is closer to the commonly cited 10 to 12% and not 16%. Here we have some of the most established photoanode materials used for water splitting, so hematite, bismuth vanadate, tungsten oxide and titanium dioxide are all chemically stable, relatively inexpensive and based on abundant elements, which makes them attractive also for large-scale applications. However, each material comes with its own limitations. So hematite, for example, has a very promising theoretical efficiency, but its extremely short hole diffusion length leads to severe recombination losses. In contrast, materials like the bismuth vanadate or tungsten oxide have much longer diffusion lengths and therefore generally show better charge collection, although they have wider band gaps and lower theoretical efficiency limits. So overall, the reported efficiencies here are still well below the theoretical limits, and this is mainly due to recombination, also slow water oxidation kinetics, and the need for nanostructuring to compensate for short diffusion length. Here, on the other hand, we have some of the emerging photoanode materials that have attracted some interest in the recent years. So compared to the classical metal oxides, many of these materials offer more favorable band gaps and therefore much higher theoretical efficiency. Perovskites in particular have achieved very impressive performance in tandem devices, and they benefit from exceptionally long charge carrier diffusion lengths. So, however, these higher efficiencies, they usually come at a cost, and many emerging materials still suffer from poor long-term stability, especially under these aqueous operating conditions, and their fabrication is often more complex and expensive. So the challenge is no longer just achieving high efficiency with these photoelectrodes, but combining high efficiency with long-term stability, low cost, and also manufacturing that is actually scalable. So here we have some classical photocathode materials, and the most established materials are cuprous oxide and silicon, and they both offer excellent light absorption, suitable band positions for hydrogen evolution reaction, and also high theoretical efficiency. In particular, silicon has a relatively small band gap and very long charge carrier diffusion length, making it a very nice choice for tandem devices. The main challenge, however, is the stability. So both materials are susceptible to photocorrosion in aqueous electrolytes and therefore require protective coatings to achieve any kind of long-term operation. And in addition, the copper-1 oxides suffer from relatively short minority carrier diffusion lengths, which limits the charge collection also. So unlike many photoanodes, the main limitation of classical photocathodes is not efficiency, but achieving sufficient long-term stability under the operating conditions. And the same trend can be seen for the emerging photocathodes. So perovskites again stand out because of their optoelectronic properties and their outstanding performance in tandem devices. Other promising candidates include organic photocathodes and castricides and various metal sulfides, and they offer tunable band gaps and the potential for low-cost fabrication. However, despite the progress that is made here, the challenge remains the same. Most of these materials still suffer from limited stability in aqueous electrolytes, interface recombination, and they often require rather complex multi-layer architectures to achieve high performance. So overall, emerging photocathodes have potential, but translating their photovoltaic properties into something that is durable remains the key challenge. Maybe to summarize a little bit here, this graph compares the photovoltage of different photoelectrode materials with their band gap. And in principle, a larger band gap allows a higher photovoltage, but the measured values are usually well below the theoretical limit. The important point here is that the achievable photovoltage is not determined by the band gap alone. It also depends on how efficiently charges are separated and collected, how much recombination occurs in the bulk and at the surface, and how quickly the surface reaction proceeds. So this is why the catalyst, surface passivation, interface energetics, and the design of the junction all have such a strong influence. In particular, buried junctions can help separate the photovoltage generation from the semiconductor electrolyte interface, and often they achieve much higher voltages than simple direct contact. So when selecting a photoelectrode material, a suitable band gap is only the starting point. The interfaces and the complete device architecture ultimately determines how much of the theoretically available photovoltage can actually be used. And before we conclude this chapter on photoelectrodes, I'd like to briefly introduce one additional concept, which is dye photosensitization. Instead of relying on the semiconductor itself to absorb light, a molecular dye is attached to the semiconductor surface. And when the dye absorbs a photon, it becomes excited and injects the electron in the conduction band of the semiconductor. So the oxidized dye is then regenerated by a redox mediator in the electrolyte, and this allows the cycle to repeat. And the main advantage here is that the dye can be tailored to absorb different parts of the solar spectrum, extending the light harvesting beyond the intrinsic absorption limit of the semiconductor. So dyes have very high absorption coefficients, so only a very thin layer is required here. And the main challenge is here the stability. So the dyes can degrade under prolonged illumination and desorb from the surface, and generally have shorter lifetime than inorganic photoelectrodes. And with that, we have covered the main classes of the photoelectrode materials currently used and investigated for photoelectrochemical water splitting. And in the next chapter, we'll move from the materials themselves to how they are integrated into different reactor architectures. Now in this chapter, we will go through the most common reactor concepts, discuss their advantages and disadvantages, and see how they've been implemented in the literature. So this overview brings together the main photoelectrochemical device architectures that have been demonstrated in the literature. And although the figure looks quite complex, the classification is based on two simple questions. First, how are hydrogen and oxygen separated? Most systems use a membrane, while others avoid membranes entirely. Second, how are the photoelectrode and the counterelectrode arranged and electrically connected? Starting on the left, type 1 systems use a membrane and a wired back-to-back configuration. The photoelectrode and counterelectrode are positioned on opposite sides of the membrane and are connected through an external electrical circuit. This architecture offers straightforward gas separation and allows each electrode to be optimized independently. Different layouts exist here, for example, with integrated photovoltaic elements or different membrane positions, but the overall concept remains the same. Type 2 also uses a membrane and a back-to-back arrangement, but the device is wireless. Instead of an external wire, the electrodes are internally connected and create some kind of compact monolithic structure. This reduces external wiring but requires a much tighter integration of all device components. Type 3 introduces a different electrode arrangement, because here, instead of placing the electrodes directly opposite of each other, the photoelectrode and counterelectrode are arranged side by side or at approximately a 90-degree angle. And the main idea is to move the dark counterelectrode out of the optical path so that it does not block the incoming light. And this provides greater flexibility for illumination while still maintaining membrane-based gas separation. And then finally, the type 4 completely separates the hydrogen and oxygen producing reactor. So each half reaction takes place in its own reactor, and the two systems are connected only electrically through so-called auxiliary electrodes rather than by ionic transport across a membrane. So this provides excellent product separation, because hydrogen and oxygen are never generated in the same reactor even. But we will come back to this architecture later when discussing a practical example, since the use of auxiliary electrodes introduces additional design considerations. The important point is that these 4 types describe the overall architecture rather than a single reactor design. So within each category, many different geometries and assembly concepts have already been demonstrated, but ultimately every architecture presents a different trade-off between illumination, gas separation, electrical integration, and reactor complexity, and no single design is universally superior. So first, one of the best known commercially available photoelectrochemical reactors is the so-called cappuccino cell. This is a 3-electrode test cell consisting of a photoelectrode as the working electrode, a platinum counterelectrode, and a reference. The quartz window on the front allows illumination while keeping the electrolytes sealed inside the cell. The main purpose of this reactor is rapid material screening. So it allows researchers to quickly measure photocurrent, onset potential, IPC, and other electrochemical properties of newly developed photoelectrode materials under well-controlled laboratory conditions. And because of its simple design and standardized geometry, the cappuccino cell has become one of the most widely used benchmark reactors in PEC community, making it easier to compare results between different research groups. However, it's important to remember that this is a characterization tool rather than a practical hydrogen production reactor. And this optimized for fundamental material studies and not for efficient gas collection, product separation, or large-scale operation. Another interesting laboratory reactor is the 3-compartment PEC reactor. So similar to the cappuccino cell, this is primarily designed for photoelectrode characterization under 3-electrode configuration. The key difference here is that it replaces the liquid electrolyte with a solid Nafion proton exchange membrane, creating a PEM-based reactor. The 3 separate compartments allow the working count and reference electrodes to be controlled independently, while the membrane provides proton transport and separates the reaction environments from each other. This architecture also enables operation with humidified gas instead of a liquid electrolyte, and making it possible to investigate gas phase photoelectrochemical systems. Although this design is still mainly intended for laboratory scale material screening, it's more closely resembles practical proton exchange membrane electrolyzer technology, and therefore provides a useful bridge between fundamental photoelectrode characterization and realistic device operation. Now let's look at some representative examples from the literature, starting with a type 1 stacked PEC reactor. So this design follows a classical back-to-back architecture where the photoanode and cathode are separated by a Nafion membrane. The reactor is assembled as a stack of individual layers, including the photoelectrode membrane, platinum titanium mesh as a counterelectrode, quartz window, body plates, and sealing gaskets. So this reactor has an active surface area of 10 by 10 centimeter, making it considerably larger than typical laboratory characterization cells. And the illumination is provided from only one side through the glass window, while the transparent membrane allows protons to pass and also light between the two compartments. This modular stack design is simple to assemble, and it can be scaled by increasing the active area or by modifying the individual layers. However, because illumination is only possible from one side, you have to be careful about optical and current collector design, because this becomes increasingly more important as the reactor grows. Here another example of a type 1 reactor is the Porto cell, which was developed at the University of Porto. And like the previous design, it uses a back-to-back electrode arrangement with a diaphragm to separate the two compartments. However, the reactor body is made from transparent acrylic, which allows illumination from either side instead of only through a single window. The modular construction here also provides easy access to the photoelectrode, reference electrode, and electrolyte connections, making the reactor well suited for laboratory studies and for testing different photoelectrode materials also. One interesting feature is that the gas collection chamber at the top allows hydrogen and oxygen to be collected separately, while the electrolyte continuously flows through the reactor. Compared with the previous stack reactor, the Porto cell places greater emphasis on optical flexibility and experimental accessibility rather than compact integration. In this slide, we see one of the largest demonstration projects in this field, which was the R₃ project, which aimed to develop scalable photoelectrochemical hydrogen production systems at low temperature. And instead of focusing on a single laboratory reactor, the project demonstrated a clear scale-up strategy, so increasing the active area from 9 square centimeters to around 1,600 square centimeters. And the project targeted more than 5% solar to hydrogen efficiency with a lifetime of 10,000 hours and a modular noble metal-free system that could eventually be scaled from watt to kilowatt applications. And although the ambitious targets here were not fully achieved, the project successfully demonstrated around 3% solar to hydrogen efficiency, stable operation of approximately 1,000 hours, and most importantly, the feasibility of the modular reactor concept. So the remaining challenges are no longer basic reactor architecture, but it was here rather bubble management, reaction kinetics, catalyst performance, and the trade-off here between stability and efficiency. Another large European project was the Photoh2, which focused on scaling type 1 PEC reactor towards a practical hydrogen production. The concept combined hematite photoanode with copper 1 oxide photocathode in a tandem configuration and used an anion exchange membrane to separate the two compartments. So one particular interesting feature was the dry hydrogen concept, as mentioned before, where the reactor operated with a humidified membrane instead of a conventional liquefied electrolyte. So the long-term goals were ambitious, with 10% solar to hydrogen efficiency and 20 years of lifetime. And the reactor models should have area of up to 1 square meter. And although these targets were not fully reached, the project successfully demonstrated the tandem concept and also the dry hydrogen architecture. They also reported a throughput efficiency of about 10%, and although this was based on their own performance metric rather than standard STH or ABPE definition, so this is taken with a grain of salt because it's hard to compare. The remaining bottlenecks were mainly the stability of the photoelectrodes and the drop in performance during long-term operation. As the device size increased, the recombination losses also became more pronounced here. The next example is a rather unconventional type 1 reactor where the photoelectrodes not flat but shaped into a hemispherical dome made from a metal mesh. And the idea behind this geometry is to increase the active surface area while maintaining illumination from essentially all directions. Instead of a flat window, the transparent acrylic cylinder surrounds the dome and allows light to reach the photoelectrode from a much larger solid angle. The porous metal mesh also facilitates electrolyte access and provides a mechanically robust current collector. And the reported reactor had an active photoelectrode area of around 500 square centimeters, making it considerably larger than typical laboratory cells. It's very interesting from an engineering perspective because this concept shows that the cell geometry itself can become a design parameter. By moving beyond just flat electrodes, one can potentially improve light distribution, mass transport, and available surface area simultaneously. However, this increased geometric complexity also introduces new challenges. So manufacturing becomes more demanding and sealing curved components is much more difficult than flat plates, and obtaining uniform catalyst or semiconductor coatings over the entire dome surface also considerably harder here. The final type 1 example I want to show here is this compact PEC reactor, which already resembles a modern electrolysis flow cell much more closely than the previous designs. And instead of using a large electrolyte chamber, the photoelectrode membrane and counter electrode are assembled as a compact membrane electrode assembly, or MEA, and this minimizes the electrode spacing and therefore reduces ohmic losses by much. And a particularly interesting feature here is the flow field design. So instead of feeding the electrolyte from a single inlet, dedicated inlet distributors and outlet collectors create here much more homogeneous flow across the active area, and this is also shown in the CFD simulations here, where they demonstrate how the flow field is optimized to achieve a nearly uniform concentration distribution over the electrode surface. The reactor body itself is manufactured from PEC, providing good chemical resistance and mechanical stability while allowing precise machining over the flow channels, and this design just supports illumination from either side, making it compatible with different photoelectrode configurations and also tandem concepts. The only type 2 architecture I will discuss today is this louvered cell, because relatively few examples of this configuration have been reported in literature. In contrast to the type 1 sandwich reactors, the photoanode and photocathode are arranged side by side, while the membrane is oriented approximately 90 degrees to the illumination direction. This allows for both photoelectrodes to remain directly illuminated without one shading the other, while reducing the overall reactor footprint. And the concept is definitely elegant from an optical perspective, but it comes with a significant engineering challenge because the membrane and flow compartments intersect at right angles, and the sealing is much more difficult than in a conventional sandwich cell where the compression only acts in one single direction. So overall, type 2 architectures demonstrate an interesting alternative layout, but they remain relatively uncommon compared to the much more established type 1 reactors. So this is an example representing a type 3 PEC reactor where the photoanode and cathode are no longer arranged directly opposite from each other, but are positioned at approximately 90 degrees relative to each other. The motivation behind this architecture is to keep the dark counter electrode completely outside the optical path, ensuring that all incident light reaches the photoelectrode without shading losses. In this particular demonstration, the reactor was developed for a bio-photoelectrochemical system employing a hematite phycocyanin hybrid photoanode in a phosphate buffered electrolyte with platinum counter electrode. And although the materials are quite specialized, the reactor engineering concept is broadly applicable. So by separating the electrodes geometrically rather than optically, the design maximizes light utilization while still maintaining ionic communication through the electrolyte. And this second type 3 reactor here follows the same general philosophy of placing the dark counterelectrode outside the optical path, but introduces an important refinement, because instead of using a single counterelectrode, the reactor employs two counterelectrode chambers positioned left and right from the illuminated photoelectrode, and this creates a much more symmetric current distribution across the photoelectrode surface. And by arranging the counterelectrode approximately 90 degrees to the incident light, the entire front surface remains available for illumination, while the electrochemical reactions are spatially separated from the optical pathway. So compared to the previous bio-PEC example, this design is much more focused on reactor engineering here. The modular sample chuck on top allows different photoelectrodes to be exchanged easily, making the reactor suitable for lab scale testing of various materials, while also maintaining reproducible flow geometry. So the symmetric arrangement of the two counterelectrodes here shortens the maximum ionic transport distance compared with a single side mounted counterelectrode, and this helps to reduce electrolyte resistance and improves current uniformity. And finally, the CoolPack reactor can be regarded as the most mature implementation of this type 3 architecture. So similar to the previous design, it uses two counterelectrodes positioned on both sides of the photoanode, keeping the entire illuminated surface free from optical shading, while maintaining a symmetric current distribution. The active photoelectrode area here is increased to approximately 50 square centimeters, demonstrating that this architecture can be transferred beyond the small proof of concept devices. And one of the main objectives of the CoolPack project was long-term stable operation. So as shown in the figure at the bottom left, the reactor has operated continuously for several hundred hours, what is making the stability and not only the efficiency a major design criterion. So from a reactor engineering perspective, another interesting aspect about this reactor is that it supports illumination from either side, which allows flexibility for different photoanode configurations while still maintaining the type 3 photoelectrode arrangement. So overall, this CoolPack reactor illustrates that type 3 architectures are technically feasible at larger scales, but they still require a relatively complex reactor geometry and longer ionic transport path compared with type 1 sandwich cells. So this is an additional complexity, and this has to be justified by the optical advantages obtained from keeping the complete illuminated area free of dark electrodes. Now the final architecture here is this type 4 reactor, which represents the most radical deviation from conventional PEC designs, I would say. Instead of separating hydrogen and oxygen via membrane, there are two reactions that occur in completely independent reactors. So one reactor performs the oxygen evolution reaction while the second produces hydrogen. And consequently, there is no ionic transport between the two compartments and there is no membrane required, but only electrical connection is there instead established through so-called auxiliary nickel hydroxide and nickel oxyhydride electrodes, which temporarily store and shuttle charge between the two reactors. So during operation, these auxiliary electrodes undergo a reversible nickel hydroxide, nickel oxyhydride redox reaction, which is shown at the bottom of the slide here. The obvious advantage is a complete physical separation of hydrogen and oxygen, eliminating gas crossover and allowing each reactor to be individually optimized without compromising gas purity. However, this comes at the cost of significantly increased system complexity. So the auxiliary electrodes have a finite charge storage capacity, and therefore they must be periodically switched between the hydrogen and oxygen compartments to regenerate their oxidation state. And this introduces additional valves, electrical connections, and operational steps that are absent in conventional PEC reactors. So overall, I would say the Type 4 architectures completely solve the gas separation problem, yes, but they replace the membrane with a much more complex charge transfer strategy based on these auxiliary redox electrodes, and this makes them an elegant concept scientifically, although the engineering complexity is considerably higher as the previous reactor types. So this is not something that I would personally consider for industrial scale up. So, and this final example is something slightly different, because I would argue that this is not actually a PEC reactor, despite being often referred to as an integrated PEC or IPEC device. So at the first glance, the architecture appears similar to a PEC reactor. However, if we look more closely, then we see that there is no semiconductor photoelectrode in contact with the electrolyte. So instead, what we have is a photovoltaic cell. It is completely isolated from the electrochemical compartment and simply provides electrical power to a conventional proton exchange membrane electrolyzer. Here we have MEA, so membrane electrode assembly, and a gas diffusion layer. And this is exactly what we would expect in a standard water electrolyzer. So this approach has clear advantages, yes. So because the photovoltaic device and the electrolyzer are independently optimized, they can operate under very high current densities, almost 900 milliamps per square centimeter under concentrated light, and they also have a very nice cooling system for that. However, from a reactor engineering perspective, I think this should be classified as photovoltaics powered electrolysis rather than through true PEC. The light energy is first converted into electricity inside a PV module and only then drives electrolysis, and the photo voltage is therefore generated by a solar cell and not by a photoelectrode that directly participates in the electrochemical reaction. So whether these systems should be classified as PEC or PV electrolysis is still debated in literature. In this presentation, I would just adopt a stricter definition where a PEC device requires at least one illuminated semiconductor electrode to be directly in contact with the electrolyte. And now I want to introduce to you our own Redeem PEC reactor, which incorporates many of the design features that we have identified through the section as desirable for laboratory scale PEC research. So like the classical Type 1 architecture, it uses a stacked membrane-based configuration, but it was designed from the beginning to be highly modular and reconfigurable, so allowing researchers to adapt the reactor to different experimental needs. The reactor is compatible with both planar FTO glass photoelectrodes and porous metal foam substrates, making it suitable for a wide range of photoelectrode materials. Unlike many literature's reactors that are optimized only for one of these configurations. Also, the illumination mode can be reconfigured, different membrane types can be exchanged, and the inter-electrode distance can be adjusted from direct membrane contact up to 1 centimeter to systematically investigate mass transport and ohmic losses. Another unique feature is the possibility to operate a cathode without catholyte recirculation. So ions are generated at a photoanode, diffused through the membrane, and provide sufficient ionic transport for hydrogen evolution, allowing the cathode chamber to remain essentially dry. Besides simplifying the reactor design by eliminating the need for high pressure electrolyte circulation loop, this also enables hydrogen production at elevated cathode pressures without requiring a high pressure electrolyte pump. And in addition to that, the reactor supports independent pressure control of both compartments. The anode and cathode chambers can each be operated between 1 and 5 bar, and the pressure difference of up to 5 bar across the membrane can also be applied. So this makes it possible to investigate the influence of pressure on PEC performance, as well as differential pressure operation under realistic process conditions. So overall, the goal here was not to build a reactor optimized for one specific experiment, but rather a flexible research platform that supports a broad range of PEC reactor development studies. If you are interested in learning more about the reactor or discussing potential collaborations, please visit our website. There you will find additional technical information as well as the contact form, and we are always happy to answer any questions. So far, we have focused primarily on photoelectrochemical water splitting, and while this remains the benchmark application for PEC, there is a growing interest in using also photo-generated charge carriers for value-added organic synthesis instead of the oxygen evolution, which brings no economical value. So organic photoelectrochemistry opens up an entirely different application space. Rather than producing hydrogen and oxygen, the objective is to selectively synthesize valuable chemicals such as pharmaceuticals, fine chemicals, or biomass-derived products. And in the next section, we will look at how new requirements influence the reactor design and where the field currently stands. Before even discussing reactor designs for organic PEC, it's important to recognize that the engineering challenge fundamentally changes compared with water splitting. Water splitting is a highly standardized reaction, so we always work with the same reactant, fixed redox potential, and universally accepted performance metrics, making benchmarking between different systems relatively straightforward. Organic PEC is fundamentally different. So instead of one reaction, we are dealing with a broad spectrum of oxidations, reductions, CC coupling reactions, and radical chemistry. We will see many examples later on. And each transformation has its own optimal reaction conditions and often requires mixed aqueous organic solvent systems with finite substrate concentrations. And as a consequence, there's no universal benchmark comparable to the STH efficiency, and reactor performance becomes strongly reaction dependent. So most importantly, the engineering focus shifts. So instead of optimizing only photovoltage generation and transport, reactor design must simultaneously address chemical compatibility, mass transport, product selectivity, and electrode stability in organic solvents. So this change in perspective also requires a different approach to evaluating reactor performance. So we still use the familiar electrochemical metrics from the water splitting whenever they are applicable. So these include photocurrent density, Faradaic efficiency, and if hydrogen is co-produced, then metrics such as STH or ABP are still relevant. However, these parameters alone are no longer sufficient. So a high photocurrent does not necessarily mean that the desired chemical transformation is occurring effectively. So instead, we have to introduce chemical performance metrics. The first is the reaction yield, which simply describes how much of the initial substrate is converted into the desired product. And equally important is the Faradaic efficiency of the target product. So here, instead of asking whether electrons produce hydrogen, we ask how many of the transferred electrons actually contribute to forming the desired molecule, and this allows us to quantify the extent of competing side reaction. And this highlights one of the fundamental differences here compared to water splitting, because in overall water splitting, the main question is often how much current can we generate, because here it's essentially only one desired product, and in organic PEC, however, current is only part of the story. We have to also ask which product is formed, how selective is the reaction, how efficiently are the electrons converted into that specific product. So consequently, the reactor optimization becomes a multi-objective problem here. And already one of the biggest differences between water splitting and organic PEC lies in the choice of the electrolyte. In water splitting, solvent is essentially fixed. Water has a very high dielectric constant, excellent ionic conductivity, is transparent through most of the visible spectrum, and therefore provides almost ideal electrochemical environments. In organic PEC, the situation is completely different. The solvent is usually not selected because it's electrochemically ideal, but because it dissolves the substrate or stabilizes intermediates or is chemically compatible with the desired reaction. And as a result, many commonly used organic solvents have much lower dielectric constants than water, which you can see in the table on the right. And this immediately creates also several challenges. So first, the lower dielectric constant generally leads to lower ionic conductivity, increasing ohmic resistance of the cell and making current distribution much more difficult. Secondly, changing the solvent also changes the interfacial energetics at the electrode surface, so double layer properties, absorption behavior, and reaction kinetics all become solvent dependent, meaning that electrode performance can change dramatically simply by changing the reaction medium. And third, many organic solvents are also not optically inert. They may absorb light themselves or become colored during the reaction, and this reduces photon penetration to the photoelectrode. And solvent compatibility becomes now a major design consideration here. An important consequence of the lower dielectric constant is also the much lower ionic conductivity. So we have stronger ion pairing, and often we have higher viscosity, and as a result, fewer ions are available to carry charge to the electrolyte. So for the reactor, this mainly means a larger ohmic resistance or IR drop, which we have discussed previously, leading to potential gradients or non-uniform reaction rates, and potentially then downstream lower selectivity. So common solution is to add supporting electrolytes, typically tetrachylammonium salts, such as tetrafluoroborates or hexafluorophosphates, and they increase the concentration of mobile ions and improve conductivity while being relatively inert, not in all reactions. However, there's a trade-off here, because higher electrolyte concentrations increases the viscosity and also modifies the electrical double layer, so it can influence the reaction itself. And besides these transport limitations, the photoelectrode stability becomes another major challenge in organic PEC, because the first reason is that changing the solvent also changes the electrochemical interface, the electrical double layer, the electric field at the surface, and the band bending inside the semiconductor. And this is all dependent. So this directly influences the charge transfer kinetics and recombination losses. The second challenge here is just chemical degradation. So organic reactions often involve like radical intermediates or other highly reactive species, and unlike water splitting, these species can attack the catalyst surface, or they can form deposits that foul the electrode over time. And as a result, the stability is no longer determined only by illumination and applied potential, but also by the reaction chemistry itself. So the consequence of these solvent mixtures also being absorbent can be lower photocurrent, of course. So another problem is that the electrolyte composition changes during the reaction, and this light attenuation is dynamic, therefore, yes. In addition, the absorbed light can be converted into heat, which can lead to local temperature increases and thermal gradients, and therefore potentially faster degradation of both the electrode and the reaction mixture. And this directly affects our reactor design. So the organic PEC reactor often uses a thin layer geometry to minimize the optical path through the electrolyte. And another possibility is backside illumination to further reduce light losses before the photons reach the photoelectrode, because then they don't need to pass the organic medium. Also, if we compare photoelectrochemistry to electrochemistry, then another fundamental difference between the two is how the reaction rate is controlled. So in conventional electrochemistry, the applied current determines how fast the reaction proceeds. So if mass transport becomes limiting, the current can simply be reduced. In PEC, however, charge carriers are generated by light, so every absorbed photon creates a hole at the photoelectrode, while the reactant first has to diffuse from the bulk electrolyte to the surface. So if substrate diffusion cannot keep up with the hole generation, excess holes accumulate at the electrode, and these holes no longer contribute to the desired reaction, but instead they promote solvent oxidation, recombination, or even photocorrosion of the photoelectrode. Therefore, the reactor design becomes essential in a way where parameters such as substrate concentration, electrode spacing, and in flow systems the residence time have to be carefully balanced so that reactant supply matches the rate of photo-generated charge carriers. Another major challenge here in organic PEC is that the substrate doesn't only simply react at the electrode, it first has to adsorb to the surface of the electrode, and this adsorption is often essential because it determines the reaction pathway and strongly influences the reaction kinetics and the catalytic activity. So in photoelectrochemistry, adsorption additionally has a role because adsorbed molecules modify the semiconductor electrolyte interface, changing the charge separation, recombination, and even the achievable photovoltage. So we have seen this in the dye sensitization, which is a direct consequence of this. So at the same time, strong adsorption is not always beneficial. Reaction intermediates or byproducts can accumulate on the surface and block active sites and cause electrode fouling, and the result of that is that the photocurrent often changes dynamically during the operation instead of remaining constant. So unlike water splitting, the electrode surface itself evolved throughout the reaction, making the surface chemistry an integral part that one has to understand in organic PEC. So while in water splitting, where the desired products are essentially fixed, organic photoelectrochemistry offers multiple possible reaction pathways, and the applied potential therefore becomes a powerful tool to steer this reaction in different directions. So by changing the bias, we can change the reaction energetics, influencing which intermediates are formed and ultimately which product becomes dominant. If the potential is too high, however, undesired side reactions and electrode degradation become more likely. So to exploit this precise potential control is essential. Integrating a reference electrode decouples the working electrode from the counter electrode, and this allows for reproducible measurements and fine-tuning of this selectivity. So looking ahead, this opens the possibility of operando control, but instead of applying a fixed potential throughout the experiment, the bias needs to be adjusted dynamically as the reaction proceeds to maximize selectivity while suppressing the side reactions. So in organic PEC, the applied potential is not only an energy input, it is a reaction engineering parameter that directly determines the product selectivity. So with these general design considerations in mind, let's now look at a few representative examples from literature. So this first example is a classical batch photoelectrochemical cell experiment. Bismuth vanadate or Wolfram oxide photoanode is used to selectively oxidize benzylic alcohols into the corresponding carbonyl compounds under visible light irradiation. And the experimental setup is intentionally simple. There's just a small batch cell with a platinum counter electrode, acetonitrile as a solvent, tetrabutylammonium, tetrafluorochlorate as a supporting electrolyte, and operation at a constant current density of 0.2 milliamps per square centimeter, which is really low. So the study demonstrates here that the concept is chemically versatile, achieving oxidation of several substituted benzylic alcohols. However, the focus here is clearly on proving the reaction chemistry rather than optimizing transport or engineering aspects. And this will be a trend that we also see in the following example. So here in the second example, we still have classical batch photoelectrochemical cell. This time it is a so-called H-type cell, which is separated by a fritted glass divider. So the goal here is to selectively oxidize HMF to FDCA, which is an important biomass-derived platform chemical for sustainable polymer production. And once again, the electrochemical hardware is relatively simple. Bismuth vanadate photoanode, platinum counter electrode. Here we have a silver chloride reference electrode and simulated sunlight. And we have a potential static operation at 0.3 volts. So the main innovation is here not the cell itself. It's clearly also the reaction chemistry, and they use a tempo redox mediator, which is introduced to improve both the reaction kinetics and selectivity by enabling multi-step oxidation from HMF to FDCA. And this illustrates another common trend in this early organic PC literature, so increasing chemical sophistication while relying on just conventional batch cell configurations. This next example pushes the chemistry even further by targeting direct CH oxidation, which is one of the more challenging transformations in organic synthesis. And despite the increased chemical complexity, the experiments are still performed in conventional batch photoelectrochemical cells. So the setup again is a bismuth vanadate electrode, platinum counter electrode, silver chloride reference electrode, simulated sunlight, and acetonitrile with lithium perchlorate as the supporting electrolyte. Also, you can never scale up reaction with using perchlorates because industrially they will never use this because it's explosive. So the study also demonstrates selective oxidation of different benzylic CH bonds. So benzylic oxidations in electrochemistry or photoelectrochemistry are not the most challenging oxidations, but nevertheless, it's striking that across all three examples we've seen so far, the chemistry evolves rapidly, but the experimental platform doesn't change for now. Our next example again demonstrates a selective CH oxidation, this time using a tungsten-based photoanode to convert cyclohexane into the industrial relevant Ka oil mixture. And like the previous study, this is performed in a batch PEC cell with the photoanode, a platinum mesh cathode, and solar simulator. And the electrolyte system is based on tert-butanol and nitric acid mixture. And what makes this interesting is that this cell is operated without a reference electrode. Instead, they just apply a fixed bias only between the photoanode and the counter electrode. And while this simplifies the experimental setup, it also means that the actual photoelectrode potential cannot be controlled precisely, as it depends on the counter electrode polarization and changes during the operation. So this is not necessarily reproducible chemistry. Here, this example demonstrates the dimethoxylation of furane, and once again, the reaction is carried out in conventional batch cell. Bismuth vanadate or tungsten photoanode is combined with a platinum counter electrode and a silver wire quasi-reference electrode. So the reaction is performed in methanol using tetraethylammonium bromide, which acts as both the supporting electrolyte and also as a bromide redox mediator. So the interesting aspect here is that the substrate is not oxidized directly by the photoanode, but instead we have a photo-generated holes, and they first oxidize bromide to an active bromine species, which then subsequently performs the selective organic transformation, and this indirect pathway often suppresses undesired direct oxidations and also lowers potentially the overpotential. So again, here the chemistry becomes increasingly sophisticated while the experimental platform is still the same. And now we move directly to CH amination of aromatic compounds, and they use a hematite photoanode here. And this reaction is again performed conventional in a batch photoelectrochemical cell. You can see even here in the picture that they just use a test tube basically, where they have the alpha hematite photoanode, the platinum wire counter electrode, and the silver chloride reference electrode, and they use a blue light LED for illumination. So again, considerably more sophisticated chemistry, but the same old laboratory scale batch cell. So here we see, in a very similar setup than previously, a photoelectrochemical CH phosphorylation. So like the previous examples, carried out in a 3-electrode batch cell with blue LED. And it's interesting here that in this publication the authors also present photos of their custom built photoelectrodes. Oftentimes they don't do that, not even in the supporting information. And yeah, considerable effort here is invested in developing new photocatalysts and reaction chemistry, whereas the reaction hardware itself is always the same. And then this last example demonstrates the alpha oxyamination of 1,3 dicarbonyl compounds, and they are using a dye-sensitized TiO₂ photoanode. And in contrast to the previous examples, the reaction here is performed in this commercial setup here, which has multiple quartz tube batch type PC cells, and they are performed without applying any external bias. So instead the photovoltage is generated by the sensitized photoelectrode alone. And this is sufficient to drive this transformation, which is very interesting, but still this is batch chemistry. This publication takes a slightly different approach, and instead of focusing primarily on new and fancy organic transformations, the authors developed a photoelectrochemical flow cell, and that is directly coupled to a differential electrochemical mass spectrometer. So the flow-through design continuously transports reaction products from the illuminated electrode to the mass spectrometer, and this allows operando detection of gaseous species with high temporal resolution. So in this work, the setup is demonstrated using the photo-oxidation of formic acid on a TiO₂ photoanode, and besides recording the photocurrent, the system simultaneously monitors oxygen and carbon dioxide evolution in real time. And although this is rather specialized and an analytical device rather than a process reactor, it represents one of the early examples on where reactor design becomes an integral part of the research. And instead of simply performing a reaction in a batch cell, the cell architecture is deliberately engineered to enable new in situ characterization. So if we now take a step from all the individual examples, a clear picture emerges. So despite the impressive progress in organic photoelectrochemistry over the last decade, the field remains almost exclusively at lab scale, and most studies employ photoelectrodes with active areas of only a few square centimeters and operate with relatively dilute substrate concentrations, and experimentally the vast majority is beaker chemistry or H-type cell chemistry, which are well suited for proof of concept chemistry, but they offer limited control over mass transport, residence time, and scalability in the end. So continuous flow electrochemical reactors are still remarkably scarce in the literature, and as a result, many of the engineering principles that have become standard in flow electrochemistry or flow photochemistry have not yet been fully translated to organic PEC. Question now is how reactor engineering can help overcome the limitations that we have just discussed, because simply transferring reactor concepts from water splitting is generally not sufficient, and because many organic solvents and reaction mixtures absorb light themselves, thin film reactor geometries become highly advantageous. So by minimizing optical path lengths, more photons reach the photoelectrode instead of being lost in the electrolyte. And at the same time, channel-based microreactor architectures provide precise control over the residence time, mass transport, and mixing, and this allows the reaction rate to be matched more closely to the rate of photo-generated charge carriers, as we discussed, reducing concentration gradients and improving the selectivity. So therefore, the future of organic PEC will likely combine the strength of flow chemistry with reactor designs that are specifically adapted to photoelectrochemical synthesis rather than directly inherited from water splitting. So this is our Redeem reactor for organic PEC based on the design requirements that we discussed earlier. And here the photoactive material is deposited directly onto a TCO glass substrate, which is a single component that serves as both the optical window and also the photoelectrode, which minimizes optical losses. The reaction channel itself is formed from a replaceable gasket, so allowing the channel thickness to be adjusted from about 0.5 to up to 3 millimeters depending on your application, and the rear plate simultaneously functions as a counter electrode, and it can be manufactured from stainless steel, nickel or copper or even graphite sheets or other conductive materials. So this allows for different overpotentials against hydrogen, as I said, depending on your application. So another advantage here is the modular design, so different inserts can be exchanged depending on the application. And we can also manufacture custom channel geometries for you. So in this example, we show here a narrow microchannel with an integrated Y mixer, followed by a dedicated mixing section and then a serpentine reaction zone. But this could also be switched out to a split and recombine reactor. So for more details, you can visit our website to see the option. And finally, so in this design, the serpentine channel provides very well-defined residence time control. By just adjusting the flow rate, you can control the residence time here, and this makes the reactor well suited for a systematic organic optimization. So if you're interested, please visit our website and fill the contact form and reach out to us. So in this chapter, we focus on photoelectrochemical CO2 reduction, and the goal here is to use sunlight to convert CO2 into energy-rich products such as carbon monoxide, formate, methanol, and hydrocarbons that are larger than C1, so C2, C3, and so on. But compared to water splitting, CO2 reduction is thermodynamically more demanding and therefore requires stronger reduction conditions. So as summarized in the table here, the required Gibbs free energy generally increases with the degree of reduction, especially for multi-carbon products. So in addition, the reaction is significantly more complex. So first, It directly competes with hydrogen evolution because both occur at around similar potential, making hydrogen a common byproduct. But secondly, the selectivity also becomes a major challenge. So depending on the catalyst and applied potential and also the electrolyte, CO2 can be converted into many different products ranging from CO to formate to even multi-carbon products. And most of these products require multiple proton and electron transfer steps. So this results in rather complex reaction pathways. And these challenges also influence the catalyst and reactor design, which we will discuss in the following slides. So first here we have again our performance metric slides, this time for CO2 reduction, and it follows basically the same principles as for water splitting, but I must account for multiple competing products. So the Faradaic efficiency is calculated individually for each product, indicating what fraction of the transferred charge forms the desired product, and multiplying this value by the total photocurrent gives you then the partial photocurrent density for that specific product. And for overall energy efficiency, the product distribution must be considered. So here the solar to fuel efficiency sums the Gibbs-free energy stored in all products relative to the incident light. And while the ABPE additionally accounts again for any applied electrical bias. So the reactor development for CO2 reduction is still at a very early stage. So in conventional electrochemical CO2 reduction, flow cells with gas diffusion electrodes already achieve industrially relevant current densities here above 100 milliamps per square centimeter for products as carbon monoxide or formate. And in contrast to that, PEC studies still rely on laboratory scale, like H cells or simple windowed flow cells, and there's no standardized reactor architecture yet. And as a result, current densities are generally below industrial standards. And the key challenge here is the CO2 transport, because the solubility of CO2 in aqueous electrolytes is low, and mass transport quickly becomes limiting, and at the same time the choice of electrolytes strongly affects selectivity of products. So alkaline electrolytes, for example, suppress hydrogen evolution very well, but also promote carbonate formation, and this reduces the carbon efficiency of the whole process. So for this reason, gas diffusion electrodes are becoming increasingly important, as they deliver the CO2 directly to the catalyst while separating the gas phase from the bulk electrolyte. And this is likely one of the key directions for future PEC reactor development in CO2 reduction reactions. So here these two publications illustrate a little bit how reactor design has evolved while following similar overall architecture. So both systems here are membrane separated flow cells with continuous electrolyte recirculation, separating the cathodic CO2 reduction from the anodic oxygen evolution reaction. And the main difference lies in the photoelectrode and the operating strategy. So the reactor on the left has a titanium dioxide photoanode under UV illumination, together with an external bias, and here they are targeting products like methanol and ethylene. And in contrast, the reactor on the right uses a silicon heterojunction photoanode under simulated sunlight and operates completely bias-free, producing syngas with a reported solar to syngas efficiency of 4.3%. And despite these improvements, both reactors still rely relatively heavy on conventional flow cells architectures. So the challenges such as CO2 mass transport, gas management, product separation, and scaling remain largely unresolved here. So here I want to introduce to you our own Redeem photoelectrochemical CO2 reduction reaction reactor. And we try to address some of the limitations that we have discussed previously. So this reactor is modular and can be a platform for both electrochemical and photoelectrochemical CO2 reduction by simply exchanging the front plate. So the same reactor can be operated either as conventional electrochemical flow cell or as PEC with an integrated optical window. And for CO2 reduction, the reactor also supports an optional third flow channel, allowing direct CO2 gas delivery in addition to the two liquid electrolyte channels. So this enables both dissolved CO2 and also gas-fed operation within the same platform. Another feature is the adjustable interelectrode gap, which can be varied from a true zero gap operation to approximately 1 centimeter, and this allows for optimization of the reactor geometry for your reaction. We can also implement a reference electrode, which enables accurate potential control. So this is particularly important in CO2 reduction, where small changes in the applied potential can significantly alter the product selectivity. So this platform is also designed with scalability already in mind. So throughput can either be increased by using larger active area cells or by constructing bipolar reactor stacks for numbering up, providing a straightforward pathway for laboratory studies to larger scale operation. So overall, the reactor is intended as a flexible research platform that can be adapted to a wide range of electrochemical and photoelectrochemical applications. And if you're interested in the reactor design or want potential collaborations with us, you can find further technical details and the contact form on our website. Okay, and before the conclusion, I would like to summarize the three major application and their design requirements which we have discussed today. So to conclude the water splitting section, reactor engineering remains one of the key barriers to commercialization, and the successful scale-up requires not only larger surface areas but also modular reactor concepts that maintain uniform current distribution and efficient bubble removal. And at elevated pressures, pressure balancing between the anode and cathode compartments becomes an additional design challenge. So based on the literature surveyed, type 1 and type 3 reactor architectures currently appear to be the most promising candidates for future scale-up. So on the other hand, organic PEC and PEC CO2 reductions are both still emerging technologies, and there are no standardized photo flow reactors. For organic PEC, this requires primarily these thin film reactor geometries to compensate, one, for the light attenuation, but more importantly for the low conductivity of organic solvents. On the other hand, PEC CO2 reduction reactions builds on many of the same reactor design principles, but introduces the additional challenge of supplying gaseous CO2 efficiently. So for this gas diffusion electrodes. Finally, in both fields, integrating a reference electrode is often essential, as you can more precisely control the applied potential and therefore influence the product selectivity. So although all three are photoelectrochemical systems, the design priorities differ considerably. So water splitting is the most mature application here. The feed is simple, reactor concepts are relatively standardized, and the main engineering channel is light utilization and also the gas management, especially for scale-up purposes. In organic PEC this introduces a much wider range of substrates and solvents, and as a result, the reactor design becomes more application specific, and selectivity becomes increasingly important. And most studies will rely on small-scale batch cells rather than standardized flow systems. That's just not there yet. And for CO2 reduction, this is the most demanding case here, because mass transport is often the limiting factor because of the low solubility of CO2, and multiple competing reaction pathways reduce the selectivity. So the reactor architectures are still highly diverse. So with all three fields sharing the same photoelectrochemical fundamentals, the dominant engineering challenge is not the same. So from light and gas management in water splitting to reaction selectivity in organic PEC, and finally to coupled mass transport, especially in multiphase, and selectivity in CO2 reduction. So this slide should illustrate a little bit the current maturity of the different technologies. We have as a gold standard the conventional electrolysis, which is already established in industrial technology, and then followed by photoelectrochemical water splitting that has reached the most maturity here, but the large-scale implementation is still limited. And for organic PEC, this is a rapidly developing field, but there are no uniform reactor concepts. So this remains batch chemistry, and there's little standardization when it comes to reactors. And finally, the CO2 reduction reactors. This is still at a very early stage with major challenges in both the reactor engineering and also the product selectivity. And with that, we have reached the end of today's masterclass. So thank you very much for your attention and for staying with me throughout this very long session. I hope I was able to show that successful photoelectrochemical systems require more than an efficient semiconductor. They depend on the careful integration of materials, electrochemistry, fluid dynamics, optics, and reactor engineering. And here at Redeem Technologies, these are exactly the challenges we focus on. And based on the engineering principles that we have discussed today, we developed our dedicated reactor platforms for overall water splitting, organic photoelectrochemistry, and photoelectrochemical CO2 reduction. So if you are working in any of these areas and are looking for a reliable, research-ready reactor platform, we'd be happy to discuss how our systems would support your work. So please feel free to reach out to me afterwards, contacting us using the details shown here. Thank you once again very much, and have a great day.